Hey there, my name is Gokul. Today, I'm going to be talking about how we can speed up inverse reinforcement learning algorithms, both in theory and practice. So let's think about trying to get this car to drive laps around this track. One way we could try to solve this problem is via imitation learning. So we get data from some expert driver driving laps around this track, and we try to get the car to do the same thing. One approach for imitation might be to roll out the learner's policy in the environment and minimize some notion of divergence to a collected set of expert demonstrations. This flavor of approach is known as inverse reinforcement learning. A way I like to think about inverse reinforcement learning is that it's effectively a GAN, but in the space of trajectories. So our generator here is a policy coupled with a world model to actually give us trajectories, and our discriminator tries to differentiate between learner and expert trajectories. So our policy update is doing reinforcement learning with the discriminator as a learned reward function, and our discriminator update is trying to solve a classification problem between learner trajectories and expert trajectories. So when we think about inverse reinforcement learning, there's both pros and cons. So on the pro side, IRL approaches are robust to compounding errors, in contrast to purely offline approaches like behavior cloning. However, they require repeatedly solving a hard reinforcement learning problem in their inner loop. And if you think about it for a second, this is a bit odd. We've reduced the easier problem of imitation to repeatedly solving the harder problem of reinforcement learning. Our key question in this work was how we can try and speed up this RL subroutine. So let's go through a concrete example of why reinforcement learning can make inverse reinforcement learning inefficient. Let's consider the learner is operating in the following binary tree MDP. So they start at the top, and at each time step, they can either go left or right. And let's say we constrain the adversary, the discriminator here, to pick reward functions that are 0 everywhere, except for one of the leaf nodes. So let's say on the first iteration, the adversary picks the following reward function. Then, to find any reward whatsoever, the learner needs to explore every single node in this tree, of which there are 2 to the h. So already on the first iteration of this procedure, we already have an interaction complexity that is exponential in the task horizon. Then, for every future iteration of this procedure, we would once again need to solve this entire problem from scratch. So, if we pause and think about it for a second, most of the interaction the learner spends during their policy search is in searching parts of the tree that the expert might have never visited. So this kind of leads to our key insight, which is that we can reset the learner to states from the expert demonstrations to reduce unnecessary exploration in parts of the state space that the expert never visits. After all, if our goal is to imitate the expert, we don't need to care about how the learner performs in parts of the state space the expert never visits. So let's think about how we could apply this insight in practice. So we're going to use a form of dynamic programming here in terms of policies. So at the first step of this procedure, we're going to consider states from the second to last time step of the expert's state distribution. Then we're going to try and learn a policy that makes a single decision, going left or right, and train a discriminator that differentiates between trajectory suffixes of length 1. If we were to solve this game, we would learn that, okay, we should go left. So we are going to lock in that policy and then back up a time step. So here we're going to again learn a policy that makes a single step decision, left or right, and then we're going to train a discriminator over trajectory suffixes of length 2. The second action will be executed by the pi3 here that's already locked in. Then we can lock in this policy and do this for the entire horizon. Observe that there are only h iterations, where h is the horizon of the problem, to this procedure, and each iteration takes a amount of interaction with the environment that is linear in the task horizon. Overall, this means we have a complexity that is quadratic in the task horizon rather than exponential. We call this algorithm MMDP, or moment matching by dynamic programming. If you want to learn a single stationary policy rather than a sequence, we also give an algorithm for this in our paper. Effectively, this algorithm is like doing inverse reinforcement learning, but changing the learner's start state distribution to be that of the expert. We see these approaches help quite a bit in practice, especially on problems where exploration is challenging, like on a maze. Here, our approaches, in teal and orange, are able to be significantly more sample efficient than a standard inverse reinforcement learning approach here in gray. We also see a speedup, though perhaps less, on problems for which exploration is less of a burden. And with that, I'd like to thank you for your time.